Hello. So now we are in week 5, I think. Week 4 and week 5. We are now going to start to think about um, doing regression. Because this is a lab, we will pass through a lot of the theory. We will skip a lot of the theory, and focus really on how it's done and how to present your data. In class, we'll be talking about the final project, which is basically a regression project based on whatever data set that you're interested in. And now's a good time to choose. Okay. So anyway, we will begin by introducing the regression commands and try to investigate what sort of statistics will come out from that regression command. So we have here R, and our code is linear regression 1, which is online. And we will use these slides here, which is week 4 and 5. Okay, so we'll take it slow, and then the next one is the more important. The next set of slides is the slightly more important. But these are the two, the meat of this class. So let's spend like a month really understanding how to do econometrics or linear OLS, ordinary least squares, using R. In particular, we'll try to focus during class on your data sets. You can do your own data. You can run the same commands that we're doing here onto your own data sets. And then you can show everyone what's going on. Right, so we will learn OLS as done in R. We will learn how to get or extract the coefficients, because that's what you're interested in. Okay, and the standard errors. I assume that you know what a regression is and how it's computed, at least arithmetically. Particularly in this very simple single regression case. We will do multiple regression in a week or two. And then we will get the coefficients and then the standard errors. So remember, we ended last time with statistical testing. We discovered, or we asserted essentially, we asserted that the coefficients are t-distributed. And you've got the average, which is the estimate, which is the coefficient, and then the measure of the standard errors of those coefficients, which is an output of the regression model. Okay. Then we will learn about R squared. Okay, R squared is a measure of fit. It tells you how much of the variation in Y is explained by all of the x's that you've included into the model. Next, actually starting maybe 2 weeks from now, we will learn about categorical and discrete regressors. For this one, we'll definitely focus on continuous regressors and how to interpret them and interpret the coefficients of a continuous regressor. And then we will do some hypothesis tests. The hypothesis test is already part of the regression output. In particular, if the null hypothesis is you're saying that the coefficient is 0. So are you testing if the coefficient is statistically different from 0? So the null hypothesis there is the coefficient is 0 versus whatever it is according to the output of that model. And then we will do some predictions. We will predict using the data and the model that we have estimated. And prediction will generate residuals. Okay, so we will estimate, the standard error of the regression is based on those residuals, and then we will plot those residuals. Okay, so we will be using a data set. We'll be using a very, very simple data set that's from R. R will have several data sets. We've already used the RICE data set, which we'll be using next week or 2 weeks from now. There's a second RICE data set, which we'll also be using. Now, let's recall first the basic regression model, single variable, very simple. On the left-hand side, you have Y, which is your dependent variable, the thing you're trying to explain. And it's indexed by I because the I's are the observations. And then you're saying that I want to explain Y according to the value of X. Again, X is also tied to an observation I, right? And then the relationship is linear such that A or alpha plus beta x is equal to y for that specific observation. And that all i's have the same beta. So we all have the same, if you change your x from xi to xj, the change between xi and xj will increase on average yi to y other j by beta. Okay, we'll talk a little bit more about the interpretation of beta and alpha in a moment. So we have I is equal to 1 through n observations. So for now, it's cross-sectional data from which n observations from n units, right? So markets and students. In the exact example we have here in R, so let's start with that. First, I'll ask you to install car data. Car does not mean vehicle. It means, I think it means applied regression analysis. Course in applied regression. And then you require it or load it. Another way to do it would be library car data. And then you load ggplot2, and then we use the Anscombe dataset. And this is the dataset that we will be using for this week, probably next week. You've got states here. So the rows of the data frame, this is a data frame. The rows of the data frame are named as the states of the United States. And the columns are the different variables. So you've got education, income, young, and urban. Okay. I think, okay, we've got this explanation for Anscombe here. It has 51 rows and 4 columns, US states in 1970. So it's cross-sectional, all of the states plus Washington, D.C. in 1 year, in the same year. So that's what cross-section means. Different observations, different units, but observed around the same time period. Here are our variables. Okay, you've got per capita education in dollars, education, income, per capita income dollars, young, proportion under 18 per 1,000, urban proportion of living in the cities per 1,000. So you can test each and every column, what they are, and they are going to be numeric. There. They're all going to be numeric. Okay, so that's our data moving forward. Now, one of the assumptions of the model is this, that the relationship between x and y is linear. Okay, and that's one of the interesting things about OLS, is that we're basically assuming that the relationship between x and y is linear, and then we are imposing that. So there are a couple of reasons why we might want to do that. One, even if the underlying relationship is nonlinear, this relationship here could still be, it's called a linear approximation to something that is not linear, right? So that's oftentimes good enough, especially since we're interested really in the average of y here, right? So OLS is particularly interested in the distribution ultimately of y as it relates to x. Now, there are other things that it's not even necessarily true that when you plot y and x, it has to be like a straight line shot. You can transform y and transform x so that when you transform them, the relationship between y and x becomes linear. So for example, you could get, instead of y, you could get y as the square root of y, or the square of y, or the log of y, right? Or the exponential of y, and so on with x as well. That you can have x as a function of some nonlinear function called maybe an exponential or a square root, whatever. So all of those things are possible. And then we can definitely include that. So for a simple example would be a quadratic term in the x. You could add another variable here, wherein b2, for example, b2 times x squared. So then it would be linear. Expressed linearly, written linearly, but the relationship between x and y, as you've written it here, will be linear. Okay. Next is the assumption of exogeneity, which is the mean of E in the population conditional on x is 0. So you should have heard of this assumption before. This basically tells you that everything here that affects everything that you included here affects y independently from E. So you can imagine there are two parts to this y, right? This one, which is the expected y given x, and then this, which is the noise term. So what this is saying is that this expected y given E is not correlated or not related to this. And these are two independent sources of data or information regarding y. So this means that the error term is mean 0 conditional on the values of all the x's for all the I units in the population. Okay. So you can interpret this as the errors in the x's are independent and unrelated. So this is an assumption, and we will assume it works. In any given data set, we will basically impose this, that for a given conditional on x, the average E is 0. However, we're talking about the population versus the sample, right? So what they're saying is that the population, this is a population level assumption on the errors. Now we can always calculate the OLS estimator. The lecture class should calculate the specifics of that manually. So we will use R to do it via the software command LM. So that stands for a linear model. So whether or not this holds, which is again an assumption, we can always calculate an OLS, because an OLS is just basically mechanically as a formula which will generate, which is generated from a minimization problem. What you're doing is you're minimizing the squares of the errors here, and then you're fitting alphas to do that by minimizing the square errors. We can talk about that again next week if that's something that people are more interested in, the theory. But basically, that's how the OLS estimator, or the betas and the alphas, are estimated in practice. We're trying to minimize the square error here. And you're making guesses in alpha and beta given x such that the e's are minimized, or the square of e's are minimized. Okay. The sum of the square of e's are minimized. Okay. Now, in a linear regression, it's a linear approximation to the true population relationship, which we talked about earlier. Under the assumptions, it's the best predictor for y given x, and if x is exogenous, it's also a causal relationship. Okay, and exogenous basically given this. Okay. So having said that, these are some assumptions basically on some main assumptions relating the model to the population. Okay, and a lot of that are maintained assumptions, and that's something that you'll have to argue about in your actual work using theory and using some kind of other evidence in conjunction with actual regression. So it's a little bit more complicated than that. So we will set aside largely the issue of exogeneity in this class. Okay, but as a concept, we'll keep trying to bring it back into the class every time. Okay, so the class isn't really about handling endogeneity, which is the opposite of exogeneity, right? The loss of exogeneity, right? The failure of the assumption of exogeneity. But we'll try to keep remembering it, because this exogeneity assumption is crucial when it comes to the interpretation of beta, because it's only when X is exogenous that you can say that X causes Y. Without the exogeneity assumption, the beta is a correlation between X and Y at best. So here are the linear model assumptions, or the OLS assumptions. Again, this is the mean zero endogeneity or exogeneity assumption. The real population model is linear. Again, under some transformations, it's robust to some transformations. The data is drawn from a random sample of the population. The error terms variance is constant. The variables in X are not perfectly collinear. So this is important when it comes to actually computing for the OLS estimates, because if it's perfectly collinear, then you cannot basically have an estimate. And then finally, it's normality, not really necessary, but important for smaller samples, because we can rely on large samples becoming normal. So given 1 through 6, OLS is the best linear unbiased estimator of the population level parameters, right? So again, you've got a population relationship between Y and X, and here you've got a sample, this data that you've got, and then you're trying to determine or figure out what the population level relationship really is. And under all these assumptions, your sample is the best linear unbiased estimator of the population level parameters. So we should talk about the notion of bias and unbiased. So an estimator is unbiased if you expect the estimator to, under repeated sampling, have the mean of those repeated samples to be close to or at the actual population variable. So this goes again, for example, because this is a sample, right? So you are sampling multiple times over many periods, right? So if this is a random sample from the population, then if you continue to sample from the population, right? And you have multiple estimates for the betas or the OLS estimates. And if you were to plot the distribution of that, then it would be distributed around the true value, which is whatever the true population value is, right? So this unbiasedness is related to the conceptual or theoretical notion of being able to resample from the population. And whenever you resample, the estimate will change because the sample will be different. But if you have a lot of different samples, and if you plot all of the distribution of all of those samples, they will be distributed around the true population level parameters. So that's what unbiased means. Now, if it's 1 to 3, it's unbiased but not the best or most efficient. So it's distributed around the true population value, but the distribution is wider. The errors are wider, right? It's possible to get a sample estimate where it's really, really far from the true population. Okay, so it's not the most efficient estimate, right? And if it's not the most efficient estimate, then you are likely to basically accept it, okay, even if it's not true, because it's likely you're likely to have really large coefficients. Okay, you're not likely, but it's possible to have. It's more possible than the standard t distribution. So if you can imagine this t distribution here, the distribution for an inefficient estimator is wider than the t distribution, and therefore it's possible to come up with a larger estimate, basically. And if you will use the usual assumptions on the standard error of the estimate using the usual standard errors, without adjusting for the for example for non-constant variance, then you are most likely to not get the correct inference, because the actual distribution of the B's is different from what you were assuming is the distribution of the B's, which is based on the standard t distribution and the residuals of the regression of the regressors. So that's what efficiency means. Okay. So again, these are two very important concepts, and I'll probably release another document basically to just really dig in the concept of what an unbiased what bias is and what efficiency means. Okay, but let's move on. And since this is a lab, we're trying to move to the actual R software. Okay. Like we said, we can usually calculate the estimator regardless of whether the assumptions of the model are met, right? So in the case of the 1x regressor, the coefficients are this. So you can literally use Excel and calculate beta. Okay, you can always calculate this unless the denominator is 0, right? So my challenge to you is, when is the denominator 0? The denominator is 0 when x doesn't change at all. Okay, when x doesn't change at all, you should calculate what the denominator is. Okay, if x doesn't change at all, and then if x doesn't change at all, this denominator will be 0. We should confirm that. And then beta will be undefined because it's going to be a number over 0. It's undefined. Now, your alpha hat, you can get that from y bar minus beta hat x bar. Okay, so these are what's called the normal equations. So you should, again, I assume the theory, you've done a little bit of this in the theory part. But essentially, once you've got the b hat, which is this, you can get the alpha hat by getting the y bar, the average of y, minus beta hat times x bar, and that's going to be your alpha hat. Okay, and then you can always calculate this. So notice that even if you chose not to have a regression with a variable x, right? Okay. Even if you had this, right, you would have to drop the x. You would have to drop the x if the x is unchanging. Okay, that's the implication of that. You'd have to drop the x if it's unchanging because you cannot estimate the beta. So if you drop this, your alpha hat is essentially what? The average of y. So that's one of the key and important things, that the intercepts interpretation is the average of y after taking out the effect of x. And if for some reason you cannot estimate the effect of x, and one reason is because x really doesn't change, so it has no explanatory power on y, right? If x doesn't change and y is changing, then there's no relationship. So in that case, then alpha hat is just equal to y bar, right? So that's the interpretation of alpha hat. It's y bar minus the effect of x, all of the x's that you've estimated, times the coefficients of the x's. Now we'll end here. The lm command. So the output, which is this, and then lm, and then formula, and then data. Okay, we will use data sets for R, which we've just done, and we haven't studied. What we haven't studied yet is the formula data class. So it's really quite easy. So you've got the y variable here, and then this one is sort of like equals this. I don't know what this is called actually. Y variable, and then this, which is sort of equals x1 plus x2. So these are the different x variables that you want to include on the right hand side as your independent variables. Right? So this is the format. In this class, for this week, we will focus on the one variable examples. It's literally y variable, this one, x variable, right? Now the output is a model data class which has many things in it. So let's run some code right now. So install car data, library car data, which we just did, data, and then we will run this command. And what we're doing is we're assigning the output of the lm command, which is a model, to the object reg. And then we will use the summary command to give us a summary of reg, which is the output of the model. So let's do that right now. So now we've got that data, just to prove it. It's right there. And then we're interested in LM, right? We're saying data equals data, right? Remember, we used data as the name of data. You can use whatever name you want. And then here's the y as a function of x. So this is literally just one x variable, which is income. And what we're doing is we're modeling education or per capita education expenditures in dollars for the states as a function of income, per capita income of the people in the state. So you do that, and then here you have reg, which is a model type or an LM type, and it's got lots of stuff in it. And look at this, there's a magnifying glass. Okay, if you click that magnifying glass, it will show up here that it's basically a reg, which is a list of different things such as coefficients, residuals, effects, fitted values, QR, call, terms, which is the formula, which you can even see it here. And the call is basically the function call. The model itself, a data frame with 51 rows and 2 columns, which is the mod, which is the data frame of consisting of education and income from the data frame. Okay, so it's got a lot of things, and we're primarily interested in this one, coefficients and residuals to start. Okay. Now, if we run the summary command, it will give us the big takeaways, right? So here's the call. Here's what we did, the model that we ran. Education as a function of income. The data happens to be data. We call it data. The residuals, here's a distribution, a shorthand distribution of the data, of the residuals, I should say. So the median is, we know the mean of the residuals is 0. And the median is -4. So there's a little bit more data on the left with the negative side. And remember, a residual is negative when income here, alpha plus beta times income, right, is greater than education, right? Because remember, the residual is, here's the E, right? So this E is negative if this one is bigger than this one, okay? And it's slightly more negative, right? Because the median means the more number of observations have a negative number, so it's on the left side. But the mean is to the right of the median, 0. Okay, so we will plot the residuals for this particular regression, maybe in the next video. Now, coefficients. So here are our coefficients: 17.71 for the intercept, and income, it's 0.05. Okay. Now, let us interpret these things first before continuing. Okay, so what is the interpretation of 17.01? The interpretation of 17.01 is, let's say that the income is 0. Okay, if the income is 0, then what is your intercept? 17.71, which means that the average education per capita education expenditure is 17.71 if income is 0. Okay, so that comes from here, right? Okay. So what is the interpretation of this guy, right? It's basically when x is 0, when x has to be 0, then alpha hat is equal to whatever the value of y is, whatever the value of y is, right? Take away the bar. Let's say it's yi and then xi, right? If x is 0, so for that particular x observation, the value of y must be equal to this. Okay. Now it's also valid for the other one, that the mean, this is the mean, okay? This is also the mean given the mean of y minus the mean of x times this coefficient of 0.05. Okay, those are two different interpretations of the intercept. And now I'm just introducing the second one, which is basically if the income for a particular observation was 0, 17.71 means that state's education per capita spending has to be 17.71. Now, you can imagine having that sort of thought experiment of an x is equal to 0 is kind of weird, right? And it's true, the income for a state will never be 0. Okay? Which is why this interpretation of the average education spending when x is 0, that's not very realistic, right? Because it will probably never happen. Okay, so you have to be mindful of the interpretation of the intercept. Next is income. So the coefficient value is 0.05. So this means that if income per capita goes up by $1, then education per capita expenditure goes up by $0.05 or 5 cents. So this has dollar interpretations here. These numbers have dollar interpretations here because we haven't not transformed the y and x's. The y is denominated in dollars. The x is denominated in dollars per person. They're both denominated in the same output, same units, dollars per person, right? So the interpretation is particularly simple. The coefficients will have interpretation of the same units. What else? Okay. So like we said, there's lots of stuff here. Here's the data. Reg dollar model. The coefficients is reg dollar coefficients. So let's do that. Reg dollar model. Okay, so this is the data set that was used, education and income. Reg dollar coefficients. Those are the coefficients that were featured in the summary. So there's lots of things to explore here. Okay. Now, here are some functions that we will use in conjunction to the LM model class. We've already seen summary, which is summarized regression output. Coefficients, which are coefficients for the regression. So let's try it. Okay. Which is equivalent to reg dollar coefficients. Residuals or resid calculates the residuals, right? And then gives it to you in terms of a vector, a numeric vector. Residuals, or resid, reg. And will give you residuals for each observation in your dataset. And since the data itself is named, each of these residuals are also named. It's a named vector. Fitted is extract the fitted values. Let's try it. So these are the predicted values for education spending. And then predict will be the same as fitted, basically, if you use existing data as your base. Okay. The difference between fitted and predict would be if you have new data and if you wanted to use the old model to predict from with the new data. Confidence interval will be confidence intervals from the regression coefficients. Okay. So what's the interpretation of this? So if intercept, the confidence interval, the 95% confidence, it's the 95% confidence interval. 0 is inside the confidence interval, right? So that means 95% of the time, the intercept would be either -40 or +75, right? Whereas for income, the coefficients will be 0.03 or 0.07. Okay, 95% of the time. VCOV is the variance covariance matrix. VCOV reg. So these diagonal variables are the variances of the coefficients. So for intercept, 833 is the variance for the intercept of 17, right? So remember, the coefficient for the intercept is 17.71, but the variance is 833, which explains really why the coefficient, why the confidence interval includes 0, because the variance is just so large compared to the estimate, such that it will definitely encompass 0. So you cannot really differentiate 17 to 0. That's the point, because the variance is that large. The variance for income is this one, 0.0007, which is much smaller than 0.05, right? Because there are 4 zeros here. This is like 100 times smaller than that one. And therefore, that's why you have this relatively narrow confidence interval for income, which is either 0.037 or 0.073. Okay, so we'll end here with plotting. And what you should really do is try to get another data set and try to use that LM model and try to get comfortable using those commands. We'll try to do that in class as well. All right. Just remember, one of the things that I have not yet emphasized is that, again, for the data, for the Anscombe data, it's in the long format because each row is an observation. Each row is a state. And several things are observed per state. So these are what you observe per observation, and the rows are an observation. So your data should really be in a long format first before you use the LM command. Okay, so we'll do a part 2 and maybe a part 3 next time.